Well, again, or new, and this is now a new topic. We have talked much about monetary policy in general, and now I want to talk about a specific model explaining monetary policy and explaining also the behavior of central banks, which is quite famous. And within this model, we will talk, and maybe you have talked about this in other lectures, about the so-called time inconsistency problem, because this time inconsistency problem, this we find in many topics in economics. This is all about expectations. When somebody moves because of given expectations of the other one, what are you then doing? And this is then called the time inconsistency problem. Have you talked in other lectures, or have you ever already heard about this topic of time inconsistency? No? Okay. Anyway, then we will do it here. And also, and this is, yeah, a very actual problem because Mr. Powell, the most powerful president of central banks in the world, has to step down. This is usual. You cannot do it for lifetime in the United States. And then there will be announced a new president. And there, to announce the new president, the right has the government in the United States. Well, and maybe you have heard that Mr. Trump is not very content with Mr. Powell. He is maybe one of the last guys who is really also in public in opposite to Mr. Trump. And he really sometimes said, well, I'm not doing what you want. And this is about independence of central bank. And also, if you look at the ECB, then also this governing council of the ECB, of the European Central Bank, is independent from the government. Well, of course, they have wishes and they also announce their wishes, but the central bank in democracies are specifically institutionally independent of the governments. Well, and this model gives us an explanation why this is maybe a good idea to do this. Because on the other hand, think about the ISLM model, where we did the theoretical calculations, and there we calculated the fiscal multiplier and the money multiplier, and both are positive. So with both economic instruments, we can push the economy, and then why not that the government is announcing a fiscal program and then says to the central bank, please do in parallel also a monetary impulse into the economy. Well, and within this model, we can explain why it is maybe a good idea that central banks are independent and independent explicitly, then we call central bankers which mainly focus, and this was the reason why Mr. Powell hasn't done what Mr. Trump wanted to have, is that in the United States we had an increase of the inflation rates, and there the opinion of Mr. Powell was, if I now push the economy by lowering the key interest rates, which even increase the inflation further. And for this, then, if we have really the main focus on inflation as a central banker, then we call them conservative. And yeah, somehow we can then also um, argue within the model which I present today why such maybe conservative central bankers are superior to discretionary monetary policy. Yeah, this model was mainly developed by Barrow and Gordon in the 1980s. This is, you see here also, just 11 pages. This is a quite simple, or simple not. It is a short, little nice model, and actually I also used this model in my PhD thesis. Mr. Barrow and Mr. Gordon, they did not obtain until now the Nobel Prize, but Mr. Kitland and Mr. Prescott, they did also much research on this general problem of rules versus discretion in monetary policy, and later on they obtained the Nobel Prize. But not only for this, they did also quite a lot on economic growth. And yeah, their paper from 1977, there you find somehow a similar model like the model of Barrow-Gordon. What I will present is the Barrow-Gordon model. Okay, so what we are doing is, and for this remember the magic square. From the introductory course of macroeconomics, and there we had economic growth and we had price level stability. Well, and in general, we see also from the data, then in, so to speak, good times, quite often we have also high inflation rates. But on the other hand, we know that too high inflation rates, they are harmful for the economy because then markets do not function anymore in the right way. So in general, we have somehow a trade-off between having low inflation rates, price level stability, and economic growth. And within our model, we then assume that we have something like a long run target of both variables. And for developed economies, economic growth maybe something in between 1 and 3%. And for inflation in general, this 2%. And then we say this is our medium or long run target. And if we deviate from these targets, then this is costly. And this costs we then the deviations, then we are modeling with a quadratic approximation. So we have an inflation target of P star, and we have an output target of Y star. And when we are deviating from this target, then we assume that the deviation costs in a functionality of a quadratic function. Well, this modeling with a square also doesn't just fall from heaven. Well, you remember maybe from statistics that their deviation from the average you also calculate with the sum of the quadratic deviations. Remember what we have done, what I have explained to you for the linear approximation. There we said, well, we have deviations from the average, and then we look at the squared deviation of the average. And yeah, in a similar way, we are modeling here our overall losses as the sum relative to our targets. But then we say, well, especially when we look at the long run target of output, there we can think of potential output, that there we are assume that our target of our economic institution is a little bit above potential output. So we multiply this with a number k larger than 1. And then, yeah, let's ask, why should we push in the short run the economy a little further than our estimated potential output? And the reason for this is we, yeah, especially know how markets function relatively to each other, and especially the labor market. And in the labor market, we know that there we have these wage rigidities, that it follows a little bit behind the commodity markets and also the financial markets. And there, then the reason is, well, to push the output a little bit further will then help the labor market to come into equilibrium. Well, of course, this K shouldn't be 2 or something like this, but a little bit larger than 1. Then this is the explanation of this additionally introduced parameter. Yeah, well, and then we say, how should we weight these two targets, the price level target and the output target, relatively to each other? And how it should be weighted, well, this we cannot calculate from a model. Should the first part be 20% and the other part 100%? And therefore, in our model, we introduce a general weight. Let's see, where did I put it? Oops, before the inflation target. So of course, I only introduce one number because I do not need another number B here, because it's only the relative weight between these two. And this would be then our general loss function. Of the central bank. Well, that my calculations later on will be not too complicated. We also introduce here just a factor of 1/2. Well, this is a loss function. This represents, so to speak, the preferences of the central bank. And you know from microeconomics that preferences or utility is just an ordinary concept. So only the row of your baskets of consumption, or here of the pairs of Y and P, is decisive. Not how large is the number. We only ask if the number of the one pair is larger than the number of the pair of the other pair. And therefore, it doesn't matter if I multiply my loss function with any number, because it only shifts the region, but it doesn't change the row. Let's say you have the row of 1, 4, 7. If I multiply every number with 2, then still 2 is larger than is smaller than 8, is smaller than 14 in the same direction as 1, 4, and 7. Why do I introduce the 1/2 here? This is a technical reason. Well, I already know that I want to optimize something in the end. And of course, the derivative of a squared function is just 2 times the function. And then you just will see that the 2 is always canceling, and I do not have to write down always this 2 when I have calculated the derivatives. Yeah. So this is just a technical reason why I introduce here my 1/2. Well, and then I already have qualitatively argued that there is a trade-off between output and inflation, and with this trade-off we have also dealt here in our lecture, and we actually quantitatively have modeled this trade-off, and this trade-off is just the Phillips curve. Remember, when we do not choose output, but we have an inverse dependence between output and unemployment, then we had these Phillips curves where we said the higher the inflation, the lower the output, the lower the unemployment. Since unemployment is inversely related to output, then we obtain a positive dependence. As I have already qualitatively argued, the higher the inflation, the higher the output. But we want to have inflation in the neighborhood of pi star. So this is then the trade-off dependence between price level stability and our output target. This is the trade-off between inflation and output. Well, and remember, the paper is only 11 pages because that's it. So this is the setup of our model. So the central bank wants to minimize their losses given the Phillips curve, and within the Phillips curve we have here the public expectations of inflation. So this is the part where the expectation of the other economic agent steps in. Inflation expectations of the public. And all this we put now together, and I will further simplify the exposition a little bit, because also, well, we know that in practice this number is 2% roughly all over the world. We find this 2 or 3%. But I think you can also imagine that conceptually it doesn't matter which number this is. the model is functioning always in the same way. So it doesn't matter if this number is 2, 3, 4. Well, then in order to simplify my calculation, then I say, well, let's set this number to 0. Because then again, I do not have to write so much. So for this, then this is the task for today and maybe also next week. I don't know if we will make it today through all the calculations. So I have, this is my loss function given in two variables. Now here you see we have set pi star to 0. So there it is, pi star equals 0, given the Phillips curve, subject to the Phillips curve, and then we have to make assumptions about how the expectations of the public are formed. And here we want to distinguish between two different concepts. And the first one is, well, let's now say or assume in general via the interest rates the central bank could directly steer the inflation rate. Well, the argumentation behind this is if we increase interest rates, then credits will be more costly, investment is going down, total demand is going down, so no demand pressure in the market, so inflation is going down. So this now we overall process we just skip and we assume that the central bank could directly steer the prices, so could directly set inflation rates. And then, well, there, if we look at the ECB, there's a protocol where we can really read in the medium term, 2% is our target. So they have announced what is their target, where they want to have the inflation rate. And then the first thing would be, well, let's assume the central bank announces its target and that we believe it, that the central bank is really doing it, that they are steering inflation so that the economy will match their target. This then would mean that the inflation expectations would be also 0, and now we assume that the central bank is really doing this because there is no law that they have to do it. They have only announced their target. But then, and therefore we call this commitment, I'm really doing what I have promised. And there maybe you also see that from this assumption arises some problem in general in politics. Before the polls, our politicians are promising many things, and after they have been elected, they're doing the opposite. So, but here we assume I do what I have promised. And this we call then commitment. So I'm announcing inflation should be at 0. I believe the institution which can steer prices, that they really set prices to 0, and then they are really doing the policy that 0 inflation occurs. But of course, think of the politicians in another economic field. we could also think of deception. And this would mean, well, I'm announcing I will set inflation to zero. I believe that inflation is set to zero. And now maybe you can directly understand the argumentation that then if I believe what they have announced, that then the central bank has an incentive to deviate. Because think of the Phillips curve, we have a positive dependence between inflation and output. And I have an output target of K times Y star, a little bit larger than potential output. Expected inflation is fixed now because the public is believing me at zero. If I know now as the financial institution push prices a little bit further than zero inflation rates, this would mean that then I can push output and then I will be a little bit more in the neighborhood of my output target. And this then means, due to this incentive, my reaction function, I will increase inflation above zero at some PT number which is larger than my target. And then the last one is that we think, well, we are all clever guys. We ask ourselves, what are all these bankers in Frankfurt are doing? And we have read the Barrow Gordon paper, 40 years old, and say, well, maybe they decide due to something like this, somehow like such a loss function. And actually, if we look into the description of the Fed in the United States, then you see that there also in this institution, it is written down. They have one target, price level stability, and then you find also an unemployment target where they have to focus. So there is actually written down that they are doing something like this here. So then, again, think of an announcement. My target is zero. I try to set inflation to zero. Now we assume, well, the public knows the reaction function. It forms its expectation due to this reaction function. And this means, of course, that the public does not believe that inflation is set to zero, but to another larger number. This means then in equilibrium expectation or in rational expectations, this here wouldn't be rational because I know that the central bank has an incentive to deviate with rational expectations. We set then pi, but this is not determined right now, but we only know that the public is forming its expectations, expecting that the inflation rate is set due to the reaction function of the central bank. And then in overall equilibrium, again also the central bank knows that the public is transforming its expectations due to rational expectations, then we can calculate an equilibrium inflation rate pi d, which we call then the discretionary case. Well, and in all three cases, then we can calculate the overall losses. And what you should show then is this range of these three. Well, that pi c is smaller than the other two is not very surprising, because there we just have set it to 0. And in the end also we see here that output is formally equal, but it is lower than in the case of deception. So then let's step in, and maybe again for microeconomics, you have already seen that, this is from the optimization method, formally the same which you have done in microeconomics. Because in micro, what have you done? You had a utility function depending on x1 and x2, subject to a given budget equals my expenditure P1 times x1 plus P2 times x2. Well, this is fixed, this is fixed, this is fixed. So this gives us just a dependence between x1 and x2. This is our target function. There maybe you have had 1 x1 to the power of 1/3, x2 to the power of 2/3 maybe. And what did you wanted to do? In this case, you said, well, I want to maximize utility. Well, from a mathematical point of view, it doesn't matter if your target is to minimize or to maximize it. In both cases, you have to calculate the derivative and setting this derivative to 0. Yeah, and I don't know if you have used different methods to solve this problem in microeconomics, but as I know this method you have definitely done, that you did it via the Lagrangian method. But also if the functions are not too complicated, and in our case we have here a linear function and if we have here a quadratic function, this is really not too complicated. What we can then do is, since this is a dependence between y and pi, we can just use this dependence to feed it into our loss function in order to cancel y or pi. And then you have only a function depending on one variable. And then, of course, you have not anymore this evil problem of calculating partial derivatives. This would be then the so-called substitution method. Or you can use the method of total differential. This we had also when we have looked at the ISLM model. So this is something like an overall derivative calculating in our case. And this total differential method, I think you have also done in your micro course, because what does this total differential method mean? In micro, this was your indifference curve, x2, x1. This was your budget line. And then you had the optimum in the tangent point. Well, the slope of the budget line was just P1 over P2. And the slope of the indifference curve this was the marginal rate of substitution, and this was just given by the relative number of the partial derivatives of your utility function. So du dx1 over du dx2. And this concept you also just get if you take the total differential of this function, saying that in the end, in the optimum, utility should not change anymore because you are in the optimum. You do not want to change it. If you could increase it further, then you are not in the optimum. So in the optimum, the change of utility should be 0. And this, I don't know if you have done this formally. This would mean you calculate this. And this we had seen. How do we calculate this total differential? Calculating all partial derivatives, multiplying with the change of the variable. So this was then du dx1 plus du dx2 dx2. And setting this to 0 in the optimum then means that dx2 over dx1 is just minus du dx1 over du dx2 is the marginal rate of substitution. I think this you have then called the first or second law of Gaussian, or yep. Okay, and all this we just now apply on our model here. So let's start with the substitution method, and yeah, due to the time, let's start with the most interesting case here of discretion. Oops. So we had, or let's copy me this one. Oops. Where is it? There. So we just feed in this y into our loss function. Okay? Then substitution method. Or I ask you, have you done the substitution method in this case also? That you have solved this to x2 is m over p2 minus p1 over p2 times x1, and then you just can put this here, and you have only a utility function depending on one variable. Okay, so you have already seen everything. So then let's use this. And I'm a stupid guy, so I just copy this and put this inside here. Um, oops. Now I'm done. And now you see that this function, all the other things, the 1/2, the a, y star, given expectations of the public, the left variable, which I can change as the central bank, is only inflation. I have only inflation left as a variable. So then what you can see here is we can a little bit rearrange this. Here we have here a y star and we have here a y star. So this would be then equals minus k minus 1 in brackets, and then we can get rid of this y star. Yeah, minus k times y star, this is what we had before here at this side, and oops, wrong bracket. There we have to have it. And minus 1 is plus 1, so plus y star. Okay? You are still in? You see what I'm doing? Hopefully. Okay. And this I want to optimize. No? Too fast? Because this is now just only substituting it into the function. Maybe you have a look at it also at home, but it is just putting the Phillips curve into the loss function. Nothing more. And now we want to take the derivative. L prime of the loss function, or the derivative of the loss function with respect to the variable pi. Here we have it. Now we take this one. What is the derivative of this monster? Mm-hmm. Yes, and this cancels. This cancels. So I'm left from this part here with almost, so a times pi. Okay? Taking the derivative of a square means putting this 2 in front of the function and decreasing the exponent by 1. 2 minus 1 is 1. So I'm left with a times pi. So the harder part is now this one here, or not really harder part. Well, what kind of rule taking derivatives I have to apply here? This is something like f of x is in brackets a times x. This would be here my b times pi plus c. This is this one here, some number. K is a fixed number, potential output is a fixed number. So any number can be positive or negative and squared. What is then f prime? 2 in the front. Yeah, okay, this would be here 1. This we can skip. And am I done? Yes. So I have to apply the chain rule. This is now the outer derivative, and now I have to calculate the inner derivative. So what is what is the derivative of a times x with respect to x? Yep, just a. So, and now you have to apply this on this part here. Yeah, plus, and the 2 I have here out of the whole bracket a 1/2. So again, the 2 cancels with the 1/2. This is the reason why I introduced this factor here. So, and then b, the outer derivative, the inner derivative, b times the bracket. So b times pi minus expected inflation minus k minus 1 y star. So, and then I again rearrange this a little bit, because in general you want to have such a function there that you have there a part depending on your variable on the inflation and a part not depending on the variable. So this would be then a times pi plus b squared times pi minus b squared times expected inflation minus b, this one, times this factor, k minus 1 times y star. And then I have here pi and pi, so I can rewrite this to a plus b squared times pi minus, I have two minus signs here, so I can write this as a minus bracket. Or is it a good choice to write it as a minus bracket? Let me just think of this. Yeah, why not? So minus b squared pi e minus b times k minus 1 plus, sorry, it's a minus bracket. So what kind of condition do I have for the first derivative if I want to minimize? Within an extremum, the first derivative has to be No. The maximum or minimum. Therefore, I'm doing this. The derivative has to be just 0. Yeah. Think of such a function, f of x. This is a maximum, this is a minimum, this is a maximum, this is a minimum. What is the property within these extremas? Well, the derivative, the tangent is just horizontal. And the tangent on your function is the first derivative. The slope of a horizontal line is 0. I hope that you have done this in school. Yeah? And I really have to say, economics is quite often about optimizing something. Maximizing profits. I would say this is the core of doing economics. We think that we are always optimizing. And this is then just a tool. How can I optimize? When I go into my enterprise and I have an idea how looks like my production function, then I can estimate via such calculations the optimum level of output, which maximizes profits, for example. So this we set to 0. And now this we solve for the optimal inflation rate. Okay? So adding this part here and then dividing by this number here. Okay? I think this I can do in one step. This is not too complicated. So then I obtain pi equals, oh, I can still take out here this b. So I obtain then b over a plus b squared. Sorry. Yeah. Times expected inflation. It's a b squared here. Plus b times k minus 1 over a plus b squared times potential output. So what do I obtain now is, as I argued on the former slide qualitatively, that the inflation of, or the optimal inflation of the central bank is depending on the expectations of the public. So this, because of this part here, is a function of the public. So I'm reacting as the central bank on the reaction of the public. How do we set our expectations, changes? How do I, as a central bank, set inflation? And therefore, this is then called the reaction function of the central bank. Well, and in order to solve this model, now we have to apply our assumptions. How are the expectations of the public are formed? Well, and here we set now rational expectations. So I, as a public, know the reaction function of the central bank. So given this knowledge, I then would say rational expectations in equilibrium for rational expectations in equilibrium, we have expected inflation is the same as the reaction of the central bank. So expected inflation equals pi of pi e. Is this understood? So this here is now not an optimizing process. This is our assumption how expectations are formed. Okay? So I have the idea, again, my target is 0. This I have announced. But also this loss function is known by the public. And they know that I am minimizing my losses. Minimizing my losses means that the central bank calculates its reaction given the expectations of the public. But the public knows that the central bank is reacting like this. So in the end, both inflation rates, the inflation rate set by the central bank and the expected inflations have to be the same. So I do not make any error. Then let's do this. So pi in equilibrium, we have pi is b squared over a plus b squared times pi plus b k minus 1 over a plus b squared y star. And now we have here the same variable, and this we have now to solve. How do we solve this? Well, we subtract this one. So then we have pi times 1 minus pi b squared over a plus b squared equals bk minus 1 over a plus b squared y star. And the last one is then dividing by this. Well, here you know also that this is a plus b squared over a plus b squared. So this and this also cancels then. Okay? So b star is a plus b squared over a times b times k minus 1 over a plus b squared y star. This cancels also, and I obtain b over a times k minus 1, oops, times y star, and this is then the overall inflation rate. And here you see also that within our model, this assumption that k is larger than 1 is crucial to obtain a reasonable outcome, because then this is larger than 0, a and b are parameters larger than 0, So this is larger than 0 overall. Potential output, we hopefully assume that this is also larger than 0. So overall, this is a number larger than 0. So I have this incentive to deviate from my announced target. And this is, yeah, what we then say, well, one has to be careful. Also, maybe at a first step, the central bank, well, let's say, I really want to have price level stability, and this is given that I have an inflation rate of 0. But then going through all these rational arguments, this is not optimal. So I have an incentive to surprise the public. But since the public knows that I have this incentive, they say, well, I do not believe this one. And this is then called the time inconsistency. I'm announcing something, but because of rational expectations, this is not believed. And therefore, this is then called the time inconsistency problem. Or some time is left. We can do this also graphically. Pi, depending on pi e, this is a positive number, but this is also smaller than 1. Okay, because I have here b squared, I have down here b squared plus an additional number. This is a positive number. So how does this reaction function look like? It is a linear line with a vertical cut of this number. So starting here, b times k minus 1 over a plus b squared. And the slope is less than 1. And what is my equilibrium condition? My equilibrium condition is that expected inflation is the same as inflation. How can I draw this equilibrium condition into my diagram? Yeah. What do you mean with straight down? Oh no, you mean that is a vertical line? No, it is. You have here pi and here expected inflation pi e. So then this is just the identity function. They have always been to be the same, so all possible equilibrium points are lying on this function starting in the origin with slope 1. Pi equals pi e. You have seen this today in your macro course. Because graphically it is the same which we have seen in the Keynesian commodity market. Okay, so and then we end up at the equilibrium inflation rate. Okay, and then we can from a political point of view, ask, well, which kind of parameters we have to change or we can change in order to come into the neighborhood of our announcement. Well, and then you see equilibrium inflation rate is inversely depending on the parameter A. Well, we cannot do very much about this potential output. This is given because of the general performance of our economy. The parameter B is also given, parameter of the Phillips curve, just here. This is also just coming out of our data. But what I can change is the preferences in the central bank. And the A was just the preference parameter, the weight in front of the inflation target. So if I increase A, then pi star is going down. Okay? Because I'm dividing by A. And this means the larger the relative weight or the focus, the more I focus on price level stability, the less is the incentive to deviate from my target. And this is then the argument for, so to speak, conservative central bankers. If I have an independent conservative central banker who doesn't give very much on this possibility to push output via higher prices, then he or she will not very much deviate from what I have promised. Okay, so I think we are quite far in the argumentation and the comparison. Then later on, there also we have to do many calculations. So I want to stop here, and later on then we make this overall comparison. That, of course, what then also comes out is that if I deviate because of this rational equilibrium, that then overall losses will also be larger than in the first case of commitment when everything is set to zero via my inflation target. So in the end, acting rational will harm the overall economy. And this, about this you can then also think over the weekend. This is then also a prisoner's dilemma which we have here. Although everybody is acting rational, we harm ourselves. And I think you have maybe in 1 or 2 lectures already talked about prisoner's dilemma, game theory. Yeah. Because in behind what we have done is just game theory here. And this is then a classical, this time inconsistency problem is also a classical prisoner's dilemma in economics. So everybody is, so to speak, doing the right things, is rational, is optimizing, and then we take a step back and see, whoa, we come into a bad situation. We could do better. Okay, but then also about this game theoretic aspect, we will talk then next week. because we have only 5 minutes left. This would be, I think, too much to start now with game theory. Okay, thank you very much.